So I've gotten a few comments and questions dealing with how to weld sockets and Allen keys and make your own tools and that sort of thing, and people asking for advice regarding that. And I thought, well, you know what, enough of you have asked about it, so why not make a video that will help all of us out understand what you're up against if you want to do something like that. Now, in the past, I'll be honest, I've made quite a lot of custom tools. Normally what happens is someone comes to me and they need like a deep well socket. Like a buddy of mine with his Harley needed a socket to get at some nut on it, and guess what, like a 20 or 30 millimeters, a really big socket, it wouldn't reach. A conventional socket wouldn't reach. The tool was not available fast enough for him to do the job. So I ended up welding a piece of pipe, a really long piece of pipe with a breaker bar on it to the socket, and it got the job done for him. So one of the great things you can do when, especially if you have a TIG welder, we're going to focus primarily on TIG welding today regarding this, but you can start making your own tools. If you need a deeper well socket and you can't get one anywhere, guess what? You can, potentially make one. It tends not to be something that's hard to do, but you need to understand a few things that's going on here before we go and just start welding all this crap together and expect things to hold together. So I tend not to do stuff like this, but I got to put a disclaimer out here because, you know, lawyers and etc. And that is, when you start making your own tools and you start welding on all sorts of tool steels and chrome vanadium sockets and all of that, the probability of something happening is always there. And we at home or in your garage or your basement, wherever it is that you're going to be doing this mad scientist stuff, is not the same as a controlled environment. And what I mean by that is you probably don't have a heat treatment oven, nor do you understand or have access to proper controls to be able to heat treat something. So therefore, whatever you make at home when it comes to fixing and welding up tools and all of that sort of stuff is simply not going to be as good, likely, as an off-the-shelf part. And to kind of help you guys remember that, I made this little drawing, this little three-dimensional drawing. This is you, that's the tool you welded together, the abomination, and then this is your eye. And the whole point of this is to tell you, you need to be careful. If you think you can simply weld together a pre-broken wrench that you had laying around or make some kind of massive breaker bar and everything's going to be fine, you put all your weight into it or multiple, giant impact guns on it, whatever have you, and that it's going to somehow just work, you got to be very careful. You don't want to wind up looking like this guy when your custom wrench blows apart and injures your eye. And by the way, your eye's going to look probably a lot worse than this. But seriously though, you got to be careful, because when you weld on higher strength alloys, you end up affecting the heat treatment often in negative ways, and that can lead to tools that are weaker than you might suspect. So that's what we're going to quickly talk about now. So I have a list here of things that you're going to want to concern yourself with if you're going to be making your own tools. Now, I wrote up here tool steel issues. Technically, a lot of things you might run into aren't going to be forms of tool steel, but this holds true for like your sockets, your Allen keys, or actual tool steels, like for, I don't know, something that you're making for a lathe, like tooling, whatever it is. This is a good list of ideas that you should concern yourself with. So the first thing is heat treatment. These sockets are heat treated from the factory. Unless you buy them from Harbor Freight, then you might not it might not be heat treated properly, but anyways, they're all heat treated, and all that means is the base material, it's formed into the socket. However, they do that through machining and dies and all of that, and then the completed sockets are then heated to a specified temperature for a particular amount of time, possibly oil quenched, yada yada yada, and it is heat treated. When you weld on something that is heat treated, that heat treatment is no longer the same. Not only is it inconsistent, like when this piece here is heated throughout it, the heat treatment is generally pretty consistent. Well, if you weld down on here, the heat treatment, not just in the area you welded, is now different, but likely further away from that weld is also going to be affected. And you need to understand that, because when you when you weld on stuff like, say, a socket or a breaker bar or whatever, you're making your own tools, you may end up with a part that is potentially more brittle than it would have been stock out of the box, or it could be softer and more likely to just spin apart, okay? And it can be very difficult to predict the results of what your weld actually did. And that is all because you are affecting the heat treatment of that part. Now, when it comes to welding stuff like sockets and Allen keys and all of that, you need to understand filler metal alloys. The two things that you need to be considering are 309 stainless and 312 stainless. Both of these filler rods with TIG welding generally will have very good success in welding sockets and Allen keys and all sorts of tooling, and that's what I generally use. Both of these fillers are commonly used to weld things like sockets and Allen keys and all of that stuff with great success, and they're both forms of stainless steel. Now, technically, a lot of like your chrome vanadium steels tend to be welded with ER80, which is basically chromoly. That can commonly be used. The problem that I have with using that and recommending that to you guys at home is that the chromoly filler tends to produce a very brittle weld, and you get rid of that via heat treatment. Well, the problem is you're not going to be heat treating these more than likely. Therefore, by sticking with that over even ER70 standard TIG wire will probably make a more ductile weld on, say, a chrome socket than chromoly filler will. So my recommendation is to stay away from higher strength fillers and stick with ER70, which again, I would not recommend that, but if that's all you have access to, generally it will work okay. The weld will probably be far more brittle than both 309 and 312 stainless. So 100% my recommendation is if you can get one of these, use one of those. Now, another thing you need to be aware of is what I call base metal dilution. And this is something a lot of people completely overlook or don't even know it exists. And this is more of a problem with TIG. With TIG welding, because you have a torch that can basically melt metal separate from your filler, you can take something like, say, this socket, put it in here, and if you don't add enough filler and you're just melting this material together, you can get what I call base metal dilution. And with base metal dilution, you wind up melting your base materials together into a weld nugget, and without enough filler, an alloy, that filler, that 309 or 312, you can produce a very brittle weld. And what you got to understand is a lot of like higher strength alloys do not like being welded with themselves, especially if you're not going to heat treat with a finished product. So in a lot of cases, when you're welding together like sockets and making your own tools, you really need to tell yourself with TIG that you must push enough filler into the molten pool so that you do not just wind up melting both pieces of base material together without enough alloy in it, because you will produce brittle welds or welds that don't perform the way that you would expect. So that's a pretty serious concern. And you got to remember with like stick and MIG welding, because that rod or that wire is both transferring heat, the arc, and basically depositing metal, that you're not going to have the base metal dilution issue that you could potentially do if you have TIG welding, where you're just like fusion welding with minimal filler. So again, make sure you push enough filler and you're not fusion welding. Never fusion weld stuff like this. You're going to be in trouble with that. Now, another thing that's a big concern that you need to understand is rapid changes in heat. And what I mean by that is TIG is a great process where you can step on your foot pedal and bring the temperature up really fast to welding temps, to where you have a molten pool, and then you can just literally let go of the foot pedal and you no longer have a molten puddle, and it cools very fast. Rapid changes in heat are extremely detrimental to higher strength alloys. It will typically make them very brittle, especially if they're hot short sensitive, okay? So if you're gonna TIG weld a socket to something, you need to tell your brain that you need to bring the temperature up slowly, So don't just ramp up to 200 amps and then cut the heat off, okay? Bring the temperature up, not fast, bring it up slowly. So slowly increase the heat. Do your welding and then slowly taper off. Do not cut the arc immediately. It's so highly likely if you just snap out of the arc immediately that you're going to develop a crack right at that point. Another major concern is what I call and what's generally known as interpass temp. You want to be mindful of how hot you actually get what you're welding. Like again, in the case of this thing right here, there's a lot of meat on this pipe, and I'm actually going to weld this later. And the socket has a fair amount of meat in it too. This would be very easy to do 5, 6, 7 passes of TIG, and I might be exaggerating a little bit there, but at least 3 passes to try and flush this sucker out in a hurry, and you think you're good. But what you need to understand is if you allow the temperature between your weld beads to exceed, I don't know, somewhere in the 600 to 700 degree area, where we'll just put it this way. If you weld on this so fast that this socket gets stupidly hot, what will happen is rather than affecting the heat treatment closer to the weld, you now could potentially affect the heat treatment in this whole socket, which could lead to failure. So what you need to tell yourself again is slowly taper into the heat, do your welding pass. It wouldn't hurt to let it to cool, not to room temperature, but cool, sub 200 degrees. Do your next pass, let it cool to around 200-300 degrees, and so on. You don't want this sucker getting to massively high temperatures by running 3, 4, 5 passes or big wide weave passes super fast, because you will affect more of the heat treatment than you need to on this, and your finished product is going to be probably crap. So keep that in mind. And I didn't put it on here, but preheating is one of those things that could come into play. Now, a socket like this is thin enough on the wall to where I don't know that a preheat is necessarily going to help. It wouldn't necessarily hurt. If you want to do that, I would recommend somewhere around a 200, no more than 300 degree preheat to the socket, and that may help the rapid cooling of that weld, especially the first pass, to where you're in a safe zone where it's not going to crack the weld immediately. And I also didn't mention on here, but cleanliness is a very important factor on this. Do not weld through a chrome coating. You must, keyword must, grind all that crap off down to clean bare metal and shiny metal, and make sure it's still not the chrome, okay? And with it clean, weld on that. Do not weld through chrome coatings or black oxides unless you have no choice. If you only have a stick welder and you're in the middle of the Afghan mountains, well, guess what? That's what you got. But let's be honest, prep work is important. All right, I think I covered enough to where we're all on the same page. Let's get to actually doing some tests to kind of get an idea of the weldability of this stuff, and then we'll actually weld them. So I'm going to do a little demonstration for you guys. Now, I've done this in other videos in the past, but it's important enough and basically relevant to what we're talking about. I really need to show you in this as well. And what we have in front of us here is a piece of mild steel scrap, and then of course our 20mm socket that's made out of a heat-treated alloy. And what I'm going to do is just make a little TIG spot weld on this, and then we're going to file it, and we're going to notice a distinct difference in the hardness of what was welded or fusion welded on this versus this material. So that's what I'm going to do now. So as you can see, both spot welds are roughly the same size. This one's a little bit bigger, but for all practical purposes, they're spot welds. Now, when I take a file to this socket, you can see I notched it. The file had no issue notching this. Now, that area that I spot welded will more than likely be a lot harder. And it indeed is. The file literally will not cut into that. And the reason is that base material that turned to molten due to the TIG torch, it has likely absorbed things like carbon and other elements that are in that steel and absorbed it into there and has become incredibly hard. It also doesn't help how fast that was brought from a cold state to hot, liquid, molten metal, back down to cool. And that is why it is so important that you do everything in your power to prevent a fast transition from cold to hot to cold. And it's also important to use fillers that don't become brittle with carbon absorption. With that said, I'm going to plug this in here. Now that this is all prepped and cleaned up, I'm going to weld it out. We're going to look at it. Now, this isn't a how to TIG weld video. I'm not going to include an arc shot of this. We will talk about the finished product, and we will also weld some Allen keys as well after I finish this. So let me get to welding. So while that socket's cooling down, I did a quick 2-pass weld on it, let it cool between passes. I took the liberty of grabbing this Allen key, grinding it clean, and doing a little spot weld here. And let me take my microphone off so you can hear this better, but I'm gonna notch this. And you can see it's biting into this key. This is definitely harder than mild steel, but it's biting into it. And when I go over that spot weld, just listen. You can just tell by the sound at how hard that is, and you can feel it. It's almost like, well, there's a hard spot on there. The file scratches it, but man, oh man, is that hard. Like I can just tell with my fingernail how hard that is. So again, this is going to be one of those things that you really probably shouldn't be welding it with ER70 and should stick with 309, 312 instead. And of course, this will be affected, the heat treatment of it, by welding it. So what I'm going to do now is weld up 2 Allen keys together just to kind of make a tool. And then we're going to end up breaking it just to see how much strength loss it has and how brittle it's become. All right, well, with this welded together, my thought is I'm going to chuck it up in a vise and put a pipe on it and break it and see if it breaks any different than, I guess, a normal Allen key, which my guess is it's probably going to be more brittle, but who knows? Let's go and break it. So up first is an Allen key out of the same set of Allen keys. I'm just going to hit this with a hammer and see if it bends. My guess is it'll probably break due to the heat treatment. And what are we really testing here? Well, it's hard to say because Allen key to key, the heat treatment might be different. So I don't really know, but it's fun to break stuff. So I got a hammer here. I'm just going to hit this sucker and let's see what happens. It actually had more ductility, we'll call it, than I expected. It kind of bent over and then it broke, but clearly if that was mild steel, it would have just bent right over. Now this isn't going to be a fair test because, well, we have a thicker wrench here, but it'll be interesting to see if this still has some give. I'll give it a fair shake and bend it away from the weld. And I'll even be a nice guy and put it near the end. All right. And yeah, I would say that our heat treatment is definitely affected there. So it actually took a full bend, which is surprising. I would have thought it would have been more brittle. But there you go. Let's go back to the welding bench. So clearly, we changed the heat treatment of this Allen key, and this kind of really proves the point that I was trying to make on keeping the heat localized as much out of the area of what's important. And that's why, like on a case of this that I welded up, I tried to keep as much heat down here on the socket, didn't allow it to get any hotter than it needed to be up here where the work is done. Therefore, the heat treatment, where you're going to be blasting bolts off with this, if this was an actual tool, would be less affected, and more or less it's probably softer here, or again, it could be more brittle depending on the alloy and how much heat you put into it. But we kind of want to keep that effect as far away from what's going to be doing the work. Now, in a case of this, would this have affected it for actual use? Well, my guess is the heat treatment right here on the end where you're actually using it might be similar, but guess what? You may not be able to put as much torque on this sucker. Now, keep in mind, I hit this with a hammer. I don't think most of you are going to be using a little Allen key that's like 1, 2, 3 millimeter like this and hitting it with a hammer all the time. So I don't see this as I guess, a detriment due to the change, but it's something to be aware of. Now, as far as this, I was successful in joining them together. I see no evidence of cracking on the welds or anything else that you wouldn't want to see. And the truth is that sockets and wrenches and most stuff like your chrome vanadium steels and a lot of tool steels for that matter, tend to weld just like normal steel or even stainless steel. And since you're using stainless steel filler like I did, the 309, 312, you are welding with stainless. But the truth is they're not difficult things to weld, it's just they require what I call attention to detail. And those details being everything I've shared in this video, where if you decide that that doesn't apply to you and you don't want to follow it, well, then you can expect to have failures and undesirable results and a big bloodshot eye due to metal debris in it. And speaking of that, I thought I would share a story really quick regarding making your own tools. A place I used to work at, an individual decided it would be a smart idea to make his own hammer and use some form of random thick hunk of steel, I guess, that was laying around the shop. Now, I wasn't there when he did this, but long story short, he tried to make a 20-pound sledge with some form of steel that was laying around, and God knows what it was. Well, he ended up hitting a pin or something a few times, and then a shard broke off of it and lacerated his face, wound up in his face, and he had to get stitches, and I believe it even had to get surgically removed. I don't remember. And the reason I'm sharing that story with you is, hey, we've all done dumb stuff, and welding your own tools can be somewhat stupid depending. Just be smart about it. It's like I always say, if you're going to be dumb, be smart about it. And now in the case of this, would I be worried that this would break? Absolutely not. If I happen to have a socket extension that I could weld onto this, I don't have any laying around here that I can afford to lose. I need them. I would weld it on there, put this on something, and just blast it until probably the impact gun failed. I know that this is not going to break off. But the thing is that's an impact gun. If you're trying to invent a new way to do things and use a 4-foot, 5-foot cheater bar with a 4-foot snipe on it, well, guess what? Something will fail, and likely it's going to be what you modified. Now, honestly, again, on this, it would probably fail on the socket end before this would ever fail. But again, be smart about it, guys. So in conclusion, what did we learn today? Well, we learned of ways that you can safely, or at least reasonably safely, weld sockets and Allen keys, and the same thing would work for wrenches and all sorts of stuff. And as long as you follow my instructions, you'll be reasonably safe. Now in this video, I covered primarily TIG, and honestly, everything that I showed you is going to be much the same with stick. You can get 309 and 312 rods with stick. The cheapest way, by the way, for 312 stainless, go to a local Menards or even online and buy what they call a problem solver rod. They typically have blue flux and they're labeled for welding anvils and leaf springs and all of that. And those rods, which are cheaper than 312 because they don't have to pay a fee to American Welding Society, are basically 312 stainless and will do a great job stick welding stuff like this. Now, MIG welding is far harder to do something like this with, simply because I don't think any of you want to spend multiple hundreds of dollars on some form of stainless spool like a 309 or a 312. 312 is very difficult to get in a MIG spool. So if you can get a mini spool of 309 with MIG wire, then do it. But my opinion is that jobs like this are best left for TIG, and then if you have no other choice, stick. I would avoid doing this with MIG, and the reason is simple. MIG has a very difficult time welding very dissimilar thicknesses of material without fusion issues. And I would be, especially with stainless, I would be very worried on something like this that it's just bridging over, because if you run hot enough, you're going to melt the socket. But you'll get good fusion in a thicker material. But if you run cold so you don't melt the socket and put too much heat in, now you're not fusing anything. So this, again, TIG number one, stick maybe if you're good at it. And stainless stick sucks to run. It's a little harder with 309 rods especially. Beyond that, if you have any comments, questions, thoughts on this, feel free to leave them in the comments. The next video I'm going to do regarding this is how to emergency repair leaf springs, and it would be in your best interest whenever that comes out to watch it as well, because there's going to be a lot of overlap to what you saw in this and a lot of additional information on how to creatively solve heat treatment problems. So that might be worthwhile to watch as well. That'll be out, I don't know, in a week or two or something. All right, with that said, thanks for sticking around. Until next time.